Hello and welcome to another video. In this video, we're going to be doing the last problem of the biweekly contest, and that's find the maximum sum of node values. And in this one, there exists an undirected tree with n nodes numbered 0, 10, minus 1. You're given an array of edges where you have a bunch of edges, and you're given a positive number k and a zero-indexed array of non-negative integers of length n, where nums I represents the value of the node. And then so you want to sum up the actual values of the node, but you can perform an operation any number of times, choose an edge, and update the values of the two nodes as follows. You take the value of u XOR k, and you take the value of v XOR k. Return the maximum possible sum of the values that you can achieve by performing this any number of times. So essentially, instead of drawing it out like this, you're going to kind of see that the edges don't really matter, and we don't need to like draw out these edges. So instead, we can just write in the values directly. So node 0 has a value of 1, and node 1 has a value of 2, and node 2 has a value of 1. And so we can perform this operation as many times as we want. So essentially what we can do is we can actually just XOR with this here. And so if we XOR both of these with 3, like if we take this edge and we XOR both of these with 3, and we'll say we use this edge already, then basically this will give us 2, and this will give us 2 because 1 XOR 3 is 2. And then that's the best we can do, right? Because now all of these are 2, so if we want to like use this edge, if we XOR 2 with 3, we'll get 1, so that's not good. Okay, and so in the second example, our values are, let's see here, it's 2 and 3. And k is 7, so there's only one edge here. So if you actually XOR both of these with 7, you get 5, I believe, here. And you get 4 here. And so that's the best you can do. And there's only one edge. And so here, in this last one, all these values are 7, so you actually don't want to do anything at all. Because XORing any a 7 with a 3 gives you a smaller number. So there's a couple operations you have to know about XOR. Yeah, a couple operations. So for one thing, knowing that like A XOR K gives you the original value. Because XOR basically, if you XOR a bunch of numbers together, you're basically just counting up the number of ones and zeros in the bits. And if it's an even number of, if it's an even number of ones, you get a 0. If it's an odd number of ones, you get a 1. And so a number XORed with itself always gives you 0, right? So this simplifies down to 0. And any number XOR 0 gives you that original number. So that's basically the only thing you really need for this problem. And you're going to kind of see that it doesn't really matter. Like the edges don't really matter at all. You know, it's a tree, so a tree, there's no cycles. And let's walk through, like, let's just make a simple tree, and let's walk through, if we do a couple of these XOR operations, what basically happens. So let's just say we have, let's actually use, like, I think we have a tree, and we can just get rid of some nodes. So we have, like, a small tree like this, and K is, we'll just give everything, like letter values instead of a number. So we'll say this is K, and then we'll say this is, like, A, B, C, D, E, F, G. So we can just use variables instead of the number. It'll make it a lot clearer. So we can basically use this operation on every edge we have. And let's see what happens if we just like go down some random path, right? Like let's say we just go down some random path of connected edges. Let's say we go like through these 4. What would happen? And then you're going to get like an intuition, and we can do a couple of examples. So if we go here, we take this edge. This value now becomes A XOR K. And this value becomes C XOR K. And we take this edge here. Now let's take this edge as well. So if we take this edge, then we're going to take this value and XOR with K again. But because C XOR K is just C, this will basically go back to what it was before, right? So C XOR K is just the original value of C. So now we take this edge. This C will go back to its original value, and now this D will be D XOR K. Now let's say we take this edge. So now this number will have this operation performed on it, which will go back to just the normal value of D. And now this will be E XOR K. So you can kind of see, like, if we choose to go down a path, nodes that we visit twice in a path, like a node, anytime we do this operation more than once, it'll just go back to its original state. And so the only things that really get affected are like the two nodes at the start and end of the path. So finally, if we do this right here, then this E will go back to the old value of E. And now what we ended up doing by doing this operation on this edge, this edge, this edge, and this edge is this A changed and this G changed. And those are the only values that changed. So that's one thing you're going to be able to notice. And you can basically connect any two nodes like this. So if you want to, let's say, change, if you want to perform this operation on any two nodes in this tree, like let's say I want to do it on A and F, I can always do that just by going down the path, right? So I just connect like this. So I would do the operation on these. Then A XOR K would be over here. And F XOR K would be over here. And all of these, this one, and this one, this operation, XOR K, would happen twice on, so they just go back to the original state. So you can take any two combinations of nodes and find a path to do this. But you might be asking, like, okay, well, what if I want to do it on this one and this one, but I also want to do it on, like, some other ones, like maybe this one? Well, then what you can do, since it doesn't really matter, like, what two nodes you choose as a pair, if there's something in between them, you can just do the operations on one of the ends and the one in between first. So you would do it like here and here to get these two to change. And then if you wanted this one as well, then you're going to have a problem because you need two, you need a pair to do this, right? Because now, like, these will both change. But now let's say I do it here. Now this will also change and this change, and maybe I didn't want to change this one. So you need a pair, but as long as you have a pair, like, if you can pick any four nodes here that you want to change. Like, we can do this in a bigger tree now that I showed that. So let's say we pick any four nodes, and it doesn't really matter. It's a tree with no cycles. Like, let's say we pick this node, this node, this node, and this node. It doesn't matter that some are in the way of each other because we can just do, like, okay, let's just do the operation here and here, and let's do the operation here and here. And then what will happen is this node has the operation done on it twice, so its value doesn't change. This operation has it done once, and this value has it done once, so these two get changed. And similarly here, this node will have the operation done on it twice, so the value doesn't change, and these two do. And you can basically do this as long as you have pairs. In this tree, you can pick any, like, you can do this as many times as you want. So let's say we have, like, even more. Let's say we don't have 6, we have like 8 or something. So let's just pick 8 random nodes, like 1, 2, 3, 4, 5, 6, 7, 8. There's always going to be a path you can build, right, to do this. So like for this one, it would be something like this, this, and this. So you can see, like, this path will change these two nodes, this path will change these two nodes, this path will change these two nodes, and this path will change these two nodes. And this is always possible. So now that we know that, like, given nodes, we can always construct a path. It turns out we don't even care about the edges. Like, we don't really care about the shape as long as we know, like, given an even number of nodes, there's always a way to perform the operations so that all those even numbers have that K operation performed on. Now there's basically, we have to figure out, like, what nodes to do this on. So if we have a number and our number is like let's think about what happens if we have a number and we XOR it with K. So our number can either go up or down or stay the same. Let's see if actually it can't stay the same because I think K, so K is non-zero. So in order for a number to be stay the same, it has to actually, sorry, it can stay the same, but there's only one way for it to stay the same. It has to be 0, right? So our number can technically be 0, but if it's 0, it doesn't really matter. Like, let's say this is 0. It doesn't really matter if we perform the operation on it with K or not, right? Because 0 XOR K will just keep giving you 0. So let's say we had, like, an odd number of numbers that we actually had to change to make it bigger. Like, let's say we had some of these. like we had 5, but this was 0. Now this is possible because we can do this and this and this. And now what will happen is this will be 0 XOR k, which will just be 0. So this stays the same, and this will be increased. So we can easily calculate, basically, instead of going through edges at all, we can just go through nodes and we can just check like, okay, what's our node value and what's our node XOR k value? And if our node XOR k value is greater than our node value, then that's a node we want to perform the operation on. And then we can just figure out like what this difference is. So essentially, like, let's say this was a node, like let's say this was like the value of 2 and our k is like 7. We can say like, okay, well, what's 7 and 2, or 7 XOR 2? So it'd be 7's like this, 2's like this. So if you XOR it, you get 5. So you see like, okay, I want to do this operation on this number. And if I do it, I'll get 5 more. So you can basically just go through every single one of your nodes and figure out like, okay, is it something I want to perform k on or not, right? Get a count for that. So we can write that. So go through all node values and count up how many nodes to perform n XOR k operation on, as well as their total. So we're just going to go through all of our values in our node array. We can just completely ignore the edges. Completely ignore. We just go through all the values in our node array. We figure out like for each value, do we want to do n XOR k? If we do, and we get a better value, we will store that in a total. And we will also count how many nodes we have. So like I said, it was in any tree, as long as you have an even number of nodes, you're basically done. Like if this is even, just add up total to previous, we can calculate a sum, like we can calculate the sum of our initial array, and we just add total to that. So add total to sum of initial array, and we're done. Now remember, if it's odd, you can't do that, right? So like, let's say I had 5 nodes I wanted to change, like this one, this one, this one, this one, this one. There's no way to have a path where all these 5 change, but nothing else changes. Because like I said, for any path, 2 nodes will change, right? For a path of length 1, let's say, these 2 will change. If it's like this, then basically now this one will go back to what it was, but now these 2 will change and so on. So there's no way to do this with an odd number. So what you have to do with an odd number is we will still add up the total, but now we have to basically figure out the actual smallest value of the change, like which one of these changes is worth the least. So when we add up these totals of these changes, we'll write down for every node that we did want to increase, like how much did it actually increase by. And we don't need to store all of them. We just need to store the minimum one, right? So let's say this increases by 3, 5, 7, 9, and 10. As we go through our nodes, we'll say like let's just say we go in some random order. So basically what's going to happen is we're going to take this node and we're going to say, okay, this changes by 3. So now our total is 3, and our smallest value, let's call it like small or something, or SM, is going to be 3. Now here, our total is 8, and our smallest value is still 3, and then we add this, so 15, smallest value is still 3, add this, 24, smallest value is still 3, and finally 34. Smallest value is still 3. So our total, if we change everything, is 34, and the smallest value that contributes to the list is this. And then you basically have 2 options. Option A is you just say, well, since this contributes the least to change, I'm just not going to change it. I'm just going to leave it as is. Option B is you have to change this node and one node that you have to decrease. So because all of these nodes are not improving, right, by doing n XOR k, they might stay the same or they might decrease. As you go through the nodes, if n is greater than or equal to n choose k, or n XOR k, we will store the smallest value here too. And so let's say for these other nodes, let's say like they decrease by some value. Let's say this decreases by like 5, 10. Let's just put in a bunch of 10s to make it easy. 10, 10, 10, 10, 10, 10, 10, 10, 10, 10. And so if you did change, you would see like, okay, out of all the nodes I'm not changing, which one has the smallest value? It's going to be this one over here. And now I have two options. I can either decrease this by 5 to get my pair, right? To get my pair over here, or I can just leave this the way it is. And it's pretty easy to figure out which one is better there, right? So you just check which is smaller, either making a node decrease or ignoring the smallest increase, right? So we can either just say, we're not going to use this node at all. We don't really care. We'll just use these 4 and we'll increase those 4. Those are possible without decreasing anything. Or we will keep this one and then we'll find the smallest node to decrease and then we'll just add those together. And so in this case, if we decrease, this will be -5 and this will be +3. So we just want to not use the node at all. But let's say this value had a value of like 1 when we decreased it, right? So if we decreased it, it only went down by 1. Then we'd want to say, okay, let's increase this and decrease this because we still get 2 more here to our sum. And that's basically the solution. So you go through all the nodes. As you go through the nodes, if the node gets decreased or stays the same, you mark that down as the smallest decrease value. All you need to do is keep track of one value. And then as you increase, every node that gets an increase, you add it to a cumulative total, and you also keep track of what's the smallest increase you can have. Then you add your cumulative total to your sum, your original sum, and then you check, do I have an even number of nodes? If I have an even number of nodes, I just return. And if I had an odd number of nodes, I either pick my smallest increase and just don't increase it at all, or pick the smallest increase and the smallest decrease, add those together. And then that's what I'm adding. And that's basically it. So let's look at the code. So here it is, really simple. So we get a sum of our numbers. And we, like I said, we don't really even care about our edges. Like you can realize you don't even care about your edges because you know everything's connected because it's a tree. So our result is the sum of our numbers, our number of nodes that so this number of nodes is the number of nodes that we're going to want to increase. So maybe not the best name. Then I kept track of the smallest difference and the smallest drop. So smallest difference is like also probably not the best name, is going to be like the smallest, when you increase everything, what's going to be the smallest increase. So maybe this is like smallest increase, and this smallest drop is the smallest decrease, set them both to infinity. Then we just go through all our numbers. So if our number x or k is better, then we're going to calculate a difference. We're going to add it to our result, and we're going to keep track of the smallest increase in this variable. And we're going to add 1 to the nodes that we want to increase. Otherwise, we just do the same thing for the smallest decrease. So we just minimize our smallest decrease. So it's going to be the old smallest decrease or the number minus this thing here. Then if we have an even number of nodes, like I said, we don't have to do anything, like we're basically done, because if you have an even number of nodes, there's always a way to build paths where you change all those nodes and nothing else. Otherwise, you have to check like what you're subtracting. And so basically, so I ended up like my total ends up being the total with every single increase. So it'll be like the starting total plus 3 plus 5 plus 7 plus 9 plus 10. And then I have a choice. I can either drop this increase or I can subtract this decrease, one or the other. And so I just check whichever one is smaller. That's the one I get rid of. So either the smallest increase, like I said, not the best variable name, get rid of that. Or I have to subtract the smallest decrease because I'm choosing to increase everything and also decrease the smallest one to make it an even number of nodes. And yeah, we can run this. And pretty good. So yeah, I think that's the main thing, is you have to realize that like when you do this operation on consecutive nodes, you're basically just reverting a node to its previous state. So if you're doing something like this, you're just reverting a node to its previous state. And if it's a disconnected path, you're still only changing 2 nodes. So on a connected path, you're like as you keep going, all the nodes that are going to have 2 edges are just going to stay the same, and all the nodes with 1 edge are going to change. And because of that, no matter where your nodes are, you can always make it so you can connect an even amount. And for an odd amount, you can take that node and connect it to some other node. And it's not necessarily that like in this case, this was this path, but let's say our smallest, let's go back a little bit. Let's say our smallest node was actually over here, Well, that would still be fine because we can just make a different path. Like if our smallest decrease was over here, then we do something like, let's use this path instead of this one. And then we can connect this one to like this one over here. So these two are connected where nothing changes. These two are connected where this one drops and this one increases. And these two are connected where there's only increases. So no matter what your tree looks like, if you have an even number of nodes, you can always make it so nothing else gets affected. So we can go through the time and space. So essentially we're just going only through our nums. So let's see what like the dimensions are here. So I think edges is like nums -1 or something. So let's see. So this is nums length. This is like O of n. K doesn't matter. Nums I doesn't matter. Edges length is, we're not even using the edges at all. Yeah, they tell you it's always a valid tree. It'd definitely be a lot harder, or at least somewhat harder if this wasn't a valid tree. Yeah, so times O of n, space. So O of 1, I think we just have like variables. We don't have any, we don't have anything saved. So yeah, always definitely, I think this is easy enough once you figure out what to do, how to do it without storing like an array or anything. Just store a cumulative total, the smallest increase, smallest decrease, pretty easy. Once you actually figure out this little trick, I think it becomes like a medium problem at best. Once you figure out like how this stuff gets affected. It is kind of hard to figure out that this stuff gets affected. So that I think that's why it definitely is a hard problem. But once you figure out this like thing, then yeah, it makes a lot of sense to do this kind of, have this solution. Can't talk. Okay, but yeah, that's gonna be all for this one. If you have any questions about like if I didn't explain anything well or anything, just let me know. I can definitely clarify whatever. And then if you did like the video, if it was helpful, please like it, please subscribe to the channel, and I will see you in the next one. Thanks for watching.